Hello. So now we'll calculate the other things in isochoric process, and we have already calculated the work done by gas in case of isochoric process. That comes out to be 0. So work done in case of isochoric process is 0. Let's make the equation for internal energy. Let's use that equation. So if you remember, the internal energy of any gas is equals to NFT by 2, where F is a degree of freedom. We have defined that earlier. It is degree of freedom. The value of F depends upon whether the gas is monatomic, diatomic or polyatomic, and N is the number of moles of that gas. Number of moles of the gas. And T is the temperature in Kelvin. So this is the equation for internal energy, whatever process you are following. So if I differentiate this equation, I'll get du is equals to Nf by 2 dt. So internal energy, change in internal energy in isochoric process becomes Nf by 2 dt. Okay. Now let's follow the first law of thermodynamics. So according to first law of thermodynamics, according to first law, we have dq is equals to du plus pdv or dwg. So let's put the value. Now we have dwg as well as the du. If we put that value there, the dq becomes Nf by 2 dt. So the heat provided to the system in case of isochoric process relates to temperature in this form. So if you provide dq heat to the gas which is following isochoric process, the temperature change which will be happening to the gas will be dt. So you can calculate that thing. The amount corresponding to dt temperature change, we can calculate how much heat was given, or corresponding to dq heat, we can calculate how much temperature change will be happening there. So this is the formula. This is the formula for dq. Okay. So that much heat, that's how the heat provided to the gas is related to the temperature. Okay. We want to do one more calculation here. If you further do the calculation here, this dq by dt, if you see, that comes out to be n f by 2. This dq by dt comes out to be n times of f by 2. Let's use 1 mole. So if I want to have 1 mole, so for 1 mole, dq by dt will be f by 2. And this is the value of dq by dt when the process was isochoric. So let's put V. So this represents this process is isochoric. So if you remember the molar heat capacity, so when we used to calculate molar heat capacity, this value is nothing but molar heat capacity. The heat required to change the temperature of a gas by 1 unit is equals to F by 2 when the process is isochoric. So this becomes the molar heat capacity. This whole value becomes molar heat capacity, meaning for 1 mole it becomes molar heat capacity in isochoric process. It becomes molar heat capacity in isochoric process. So this whole value, this dq by dt at constant volume, we will be writing this whole value as Cv, which comes out to be equals to F by 2. Okay. So Cv, the value of Cv becomes F by 2, which depends upon whether it is a monatomic gas, what kind of gas we are using. So that's how we calculate the molar heat capacity for isochoric process also. Okay, so we have a ready-made relationship between the Q and the temperature. So we have a ready-made relationship between the U and temperature as well as the Q and temperature. So dQ becomes Cv dt. If you want to calculate the heat, if you want to calculate heat required in isochoric process, you can directly utilize this formula, and from there you can directly calculate the heat required to change the temperature. Okay, thank you.